Once again, very good afternoon, everyone. This is the second session of online training program, online GATE training program 2022. A lecture on engineering mechanics will be delivered by Professor Kanmani S S, Assistant Professor, Department of Civil Engineering, Vidyavardhaka College of Engineering, Mysuru. I welcome you to the session, madam. Professor Kanmani has completed Bachelor's of Engineering from PES College of Engineering, Mandya, and has earned her Master's from Siddhaganga Institute of Technology, Tumkuru. She has presented a couple of conference papers and good number of journal papers in both national and international level. The speaker has bagged Best Technical Paper Award in the international conference held at St. Peter's College in Chennai. With this brief introduction, I hand over the session to you, madam. Over to you, madam. Thank you.
Thank you, Raghavendra sir. It was indeed a simple and very best introduction about me. Thank you for that. So without any delay, I would like to go start the session directly. We have plenty of information about engineering mechanics. So let me start the presentation. Hope my presentation is visible. Avinash sir, is it visible? Okay. So let me start the presentation. So engineering mechanics, basically one of the most important fundamental subject that we all know. I'm going to give you very brief idea about engineering mechanics because since it's a huge subject, I cannot explain everything in just 1.5 hours. I'm trying to give my level best to give the main important principles, basic principles and assumptions, along with the equilibrium of for coplanar, concurrent and non-coplanar, non-concurrent force systems. Along with that, I'm going to give a brief introduction or briefly explain, going to explain briefly about the free body diagram, as well as going to solve few numerical problems. So let me start with the very basic assumptions that we have in engineering mechanics, that's rigid body. Every one of us know what is a rigid body, but there is a small misconception about this rigid body. So we all know that rigid body is something. I have given an example here, a rock mass, where the distance between two particles, say I'll mark it as A and B, the distance between these two particles will not change even with the application of force. For example, if somebody applies certain force on this so that this rock moves to another stage like this, even then the distance between A and B should not change. If so, this body is called as rigid body. However, there is no such body in the universe which is completely rigid. But all the bodies in the universe acts as rigid to certain extent, up to certain limit. So that limit everyone knows that's up to the elastic limit or even up to the proportionality limit. For exactly, to be precise, we can say up to proportionality limit, all the body acts as a rigid body. So here we are taking the buildings, basically the statics. In the statics, our main assumption is to think that all the bodies are linear and they are rigid. By that, when I apply load, it will not take any kind of local deformation. Instead, it completely moves from one position to another position. So what is the other body we have? Deformable bodies. So deformable bodies we usually study in strength of materials. So it is famously called as SOM. Every one of us know what is this deformable body. When we apply even a small little amount of force, it takes deformation. Such bodies are called as deformable bodies. In turn, I can say the body after proportionality limit acts as a deformable body. This is actual truth of every body in this universe, every matter in this universe. But we assume, to a certain extent, we assume that the body is well within the proportionality limit and we take that as a rigid body. So we are in this complete 1.5 hour session, I'm not going to consider the deformable bodies. I'm going to talk only about the rigid bodies. So moving on to that, the principles, basically I'm going to talk about the 4 basic principles of these forces that we have. So the forces that is applied on the rigid body. See, when we have a transmissibility of force, that is, when we have a force which is acted on a rigid body, see, this is a rigid formable body, for deformable body, this transmissibility of force will not hold good. That means it is not applicable to deformable bodies. So principle of transmissibility of force is applicable only to the bodies which are rigid. So when we the according to this principle, it is told that on a rigid body, when a force is applied, it this force tries to move this body on its own line of action of force. Line of action of force. So on this line of action of force, this force F tries to move this rigid body. What is this principle of transmissibility tells us? Instead of applying this force, remove this force, apply the same force anywhere on this line of action of force, the effect remains same. For example, imagine this is a 10 kilonewton load applied on a rigid body. It moves with an acceleration of say some 2 meter per second square. The same thing, if you remove this 10 kilonewton and apply somewhere in between the rigid body, and this is also equal to 10 kilonewton, the effect will not change. It will also create 2 meter per second square acceleration, because we have kept the force magnitude same and we have applied on its line of action of force on the rigid body. So this principle is called as principle of transmissibility of force. So this is helpful for us to draw the free body diagram, to understand the concept of free body diagram and to apply Lami's theorem. It is very helpful for us. So now moving on to the next principle, it's called principle of physical independence. The principle looks very simple. It just says that a force of F1 creates A1. A1, say it's an acceleration created by force F. I'll call this as certain effect, some kind of effect. It may be acceleration, translation, or rotation, anything. So F1 creates A1, which is the effect of force F1. On the same line, F2 creates A2. What is A2? A2 is an effect created by F2. So what this physical independence tells that when I apply F1, F1 creates A1, and this A1 is independent of F2. When these two forces act simultaneously, both A1 and A2 effects are acting. But remember one thing, F1 creates only A1, whereas A2, which is effect created by F1. A2 is independent of F1. That is our principle of physical independence. So A2 is independent of F1. That means A2 doesn't have anything to do with F1. If you remove F1 also, A2 will remain same. A2 depends only on F2. That is physical independence. Moving on to the next principle, it says principle of superposition of forces. That it says force F1, it is very similar to physical independence. Force F1 creates A1, force F2 creates effect A2. When these two forces together added on a rigid body, it creates an effect which is equal to sum of the effect created by each individual forces. I repeat, the total net effect acting on a body, this is the net effect acting on a body, is equal to sum of effect created by each individual forces. This is principle of superposition of forces. See, this is one of the most important again, which gives us the formula for resultant equations, which gives us the formula, the most famous formula of superposition, delta L is equals to delta L1 plus delta L2 in strength of materials. So these are very basics and very important, most important principles, which we usually forget once we complete the graduation. So I'm just giving the brush up. This you might have studied this in the very first or second semester in the physics cycle. So moving on to the resolution of forces. So resolution is nothing but resolving, or I can say splitting. So simply, resolution is resolving or splitting, where the given force is resolved into its components along x and y direction. So here I have taken four forces here. I'll take force F1 first, which is in the first quadrant. Now, if at all, if I want to uh, if I want to write the components of force F1, all that I will do is I'll go to the tail of the force and I will draw a line here which is parallel to x-axis and another line here parallel to y-axis. Observe that and just write the arrow marks that we have here. parallel to that. So this is positive x, so I'll call this as f1x, this is as f1y. Or simply I can write like this. If you have a force F1 like this, you have to write two parallel line, one parallel to x-axis, another parallel to y-axis, start from the tail, move towards the arrowhead. I repeat, start from the tail, move towards the arrowhead. That's how I have to put the signs or the directions to get these directions. Either I can write like this or like this. Okay, this angle, if it is say theta, just observe by this triangle. If I apply cos theta, it will become adjacent side by hypotenuse. Thereby, if I want this component fx1, which is equals to f1 cos theta 1. Likewise, this side, if I apply sine theta, it will become opposite side by hypotenuse. So I'll get fy1 is equals to f1 sine theta 1. Or here only I can write, so f1x is equals to f1 cos theta 1. Likewise, f1y is equals to f1 sine theta 1. So always remember, to apply this concept easily, you take theta always with respect to horizontal. If you take theta with respect to vertical, then you should change this symbols, or change this algebraic functions, that is sine theta and cos theta will be interchanged if you take the angle with respect to vertical axis. So I'll go to F2 now, which is in the second quadrant, which clearly indicates that your x-axis is minus axis and your y-axis is positive axis. So I'll write two lines, one in positive y-axis. So this will become f2y, another in negative x-axis, which clearly indicates it goes in negative x-axis. So f2x, if this angle is theta, always angle adjacent to theta is always cos component. So it will become f2 cos theta, and angle opposite or the left out side, we are going to get f2 sine theta. So adjacent to angle is always cos theta, opposite to the angle is always sine theta. This is the concept we usually use. So again, I will take here f3, which is in quadrant number 3. I'll write two parallel lines to x and y axis like this. Then right here, see, in this third quadrant, both x and y coordinates are negative. So I'll write the negative directions of x, negative directions of y. This is f3y. Again, if the angle is with respect to horizontal, then adjacent to angle, we are going to get f3 cos theta, and opposite to the angle, that is this side, which is very similar to this, that means having the same scale here, I can write it here. So f3y is directly equal to f3 sine theta. Or else put this type of triangle, you'll get the same answers. Now again, in the last quadrant, that is fourth quadrant, I'll write two parallel lines, one parallel to x, another parallel to y. So this is f4y and this is f4x. If this angle is theta, again, adjacent side to the angle. See, I'm not mentioning that all the horizontal components are cos theta. Remember this, adjacent side to angle is always cos component. So this is f4 cos theta, and this is f4 sine theta. It's just a brush up of the first year syllabus that you have studied. So before going to the problems, I would like to give just the brief introduction about what we have studied as basics and fundamentals in engineering mechanics. Now I'll move to the next topic called composition. So in the previous, resolution is nothing but splitting, where we are going to split the force into its components, whereas in the composition, we are going to combine that into a single force. How we can do it? So in the previous case only, I told you if this is force F, so I can write it in the form of a triangle. If this is theta, this is tail of the force, start from the tail, move towards the arrowhead. Or I can write this force here. Okay, nothing will change. So this is fx, this is fy. Same thing is written here, such that this fy is emerging from the tail point of the force. Okay, both are same. So just by applying Pythagoras theorem, observe this or this. Just by applying Pythagoras theorem, this height is equal to this. So I'll call this as fy. By applying Pythagoras theorem, if this is resultant r is equals to square root of fx square plus fy square. Just applying Pythagoras theorem. If you want theta value, theta is simply, observe, theta doesn't have anything to do with the direction of force. I repeat, theta doesn't have anything to do with the direction of force. It gives the direction of resultant directly by having or by knowing the distance of fy, or the scale of fy and fx, or the magnitude of fx and fy. So I can simply apply tan theta here. If I apply tan theta here, tan theta is simply opposite side by adjacent side. That is fy by f theta. Sorry, fy by fx. Or I can write theta is equals to tan inverse of fy by fx. This magnitude clearly indicates that don't take whether this fy and fx plus or minus direction, don't take plus and minus, just write fy and fx as it is. That's about composition of forces. So next I'll go with the last principle, that is resolved parts, principle of resolved parts, which tells that if you have forces like this, two forces which are acting on a barge here, we have a barge or a big ship, or a ship and which is drawn to the harbor through some tugboats. Two tugboats are dragging this barge. So when this is happening, so we have two forces applied through the ropes of the tugboats, F1 and F2. So all that we know that the resultant is nothing but a single force which I can replace with the n number of forces acting to give the same effect. So something like if you have F1 and F2, you can remove F1 and F2, just write Fr, which is equal to of sum of F1 and F2. So I have to create equal effect of F1 and F2, for which what I will do is I will resolve force F1 and F2. Okay, just like as we did here. So I'm going to resolve force F1 and F2. That's the first step. Just resolve F1 and F2. Resolve, if you resolve, you will get F2, and here also you will get F2y and F2x. Here you will get F1x, and here you will get F1y. This is F1y and this is F1x. Okay, when you get such thing, all that you're going to do is whichever is in the same parallel lines or same direction, say y direction, you're going to add it. If it is in the same direction, you're going to add. If it is in the other direction, you're going to deduct. So finally, you're going to find what is summation fy. At the same time, you're going to find out what is summation fx. So what this principle of resolved part says is, if you take the sum of these components along its x and y direction, these sum will be equal to component of their resultant. Say we have resultant somewhere here like this. Okay, if you find out the component of resultant, it will be something like ry, rx. Simply they say, so summation fy is our f1y difference of f2y, and this one also f1x plus f2x. So both are moving towards the negative direction, so I'll put minus here. So this is summation values. So what they simply say in resolved parts is, it says that sum of all the forces, all the component of forces along any direction, say y direction, is equal to component of their resultant along the same direction. That is your ry is equal to summation fy and rx is equal to summation fx. So find out sum of all the forces, component of forces along any direction, and you can equate this to the component of resultant along the same direction. If this is x, then this will be equal to x, with which you can apply. So if you have Rx and Ry, if you want R value, all that you're going to do is apply Pythagoras theorem. Okay. So if this is Ry, this is also equal to Ry. So you're applying Pythagoras theorem. R is equals to square root of Rx square plus Ry square. Okay. Rx is nothing but summation fx. Ry is nothing but summation fy. Substitute, you will get this formula of resultant. So what is the resultant? Resultant is that single force which gives the same effect as number of forces acting on any body. So to find it, we are going to apply first resolution of forces, then we are going to apply the Pythagoras theorem and principle of resolved parts to get the resultant value. At the same time, we are applying tan formula from algebra to get what is alpha. Alpha is the angle or the direction of resultant with respect to horizontal. Alpha is always with respect to horizontal if we are taking summation fx and summation fy. Okay, that's about the resultant of coplanar concurrent force system. Now moving on to equilibrium. So here I said that the tugboat has to move towards the harbor, which may be here to the left. So this boat or this ship or this barge was dragged by the tugboats towards the left hand side. But if I want to make sure that this ship should not move anywhere, it should stay in that position, then I have two options. Either I can make this resultant force Fr, or I can say this as R to make it equal to zero, or I have another option, apply another equal and opposite force to this side, which is called equilibrant. Okay, equilibrant, whose magnitude is equal to resultant but opposite in direction to the resultant, then the body will not move. So equilibrium has two conditions. Number one, apply a force which is equal in magnitude to the resultant but in the opposite direction, and that force is called as equilibrant. If you apply that equilibrant, the body comes back to its rest position, which is called equilibrium position. It is completely balanced. All the forces are balanced. The body will not move. It is in the same state. Okay, but another condition is that you can make R is equals to the zero, that is resultant equal to zero, to make the body to come and sit in its equilibrium position. So with that, if I take another example of equilibrium, say I'm going for equilibrium of only concurrent system I'm talking now. For concurrent system of equilibrium, I'm taking two-dimensional body. This is a two-dimensional body which has x-axis, which has y-axis, and the z-axis is perpendicular to this system that you're watching. So perpendicular means exactly perpendicular to the mobile or laptop or whatever you're watching through. So this is x, y, and this is z axis. So observe this ball, sliding ball. Everyone might have played this game. This sliding ball can move in the horizontal direction, or just it can be jumped in the vertical direction, or it can be thrown like this. You know this direction. It goes like this, it hits and comes back. So it can rotate. This is rotating. So this is rotating. It can rotate. Now, in which direction? Let me see. It can move in the horizontal x direction. This is force. Force is moving in the x direction. This is Fx. Another one, the force can move in the y direction. But it cannot move in the z direction. Z direction means perpendicular to this system. Perpendicular to the system, the body cannot move. That means your Fz will not come. Okay. On which axis? It is rotating about the axis which is perpendicular to the system. That means it is rotating about z axis. That means it creates mz. So if you want to make a two-dimensional object to settle in its equilibrium position, then make sure that its horizontal motion, vertical motion, and a rotation about its z axis are equal to zero. If these three things are equal to zero, then automatically the resultant force will be equal to zero. Once the resultant is zero, the body will be coming under the state of rest or equilibrium. Now, giving another example, the most famous, we all know this video game, so Mario. So coming to this Mario game, this Mario, again, he can move in the x direction, he can move in the y direction, and he rotates or jumps like this about the z axis. So that is mz. So if you want to keep this Mario in its original position in the state of rest, then make sure that fx equal to 0, fy equal to 0, and mz equal to 0. That's about equilibrium of concurrent force system. Now moving to the next slide. I'm going for equilibrium of non-concurrent force system. Let me take an example of a Rubik cube that we all know. If this Rubik cube, I'll take the front view of the Rubik cube. This is a Rubik cube. So this Rubik cube has all three dimensions which are predominant. So I will take this as x-axis, this as y-axis, and even z-axis also exists for this. So z, x, and y. So if I write like this, z-axis. So it has all three axes in it. So how to keep it in its rest? So I can move this body or move this cube in fx direction, in the fy direction, or in the fz direction. That means it creates translatory motion in x, y, and z direction. Along with that, check out, this is the motion, this is the rotation that's happening in the Rubik cube. So the rotation can happen in this vertical direction or horizontal direction. So this is moment along y direction, moment created along y direction. So if I take this axis is y axis, just a minute. This axis is y axis, but the force is m. Just a minute. Yeah, this is m y. On the same line, if I move ahead, now see this body is rotating about z axis. So this is m z. Now this body is rotating about x axis like this. So this is m x. So we have three forces. We have three forces and three moments. So if you ensure that in all six directions, if the body is maintained in such a way that the forces and moments are equal to zero, then the entire cube is said to be in the state of rest or equilibrium. Now, moving to the next part, I have taken one natural example that we all see, the stack of stones. So, coming to this stack of stones, if you observe, if you want to stack the stones one above the other, you knowingly or unknowingly making that the body should not move in the x direction, y direction, or should not rotate in the z direction. You are ensuring that it's not rotating in any direction, it's not moving in any direction. So it is balanced on one position and you're stacking the stones on the same position, one above the other. So that is through non-concurrent, that is where we are going to tell the equilibrium of non-concurrent system, where the force can be applied in all three directions, but we are making it sure that the body will not move in any direction. This is just a stack of stones I'm showing, but when you see the actual field, all the structures, whatever we see in reality, whether it is a natural or man-made structures, if it is in the state of rest, it should obey these six equations of equilibrium. So that's about equilibrium. Now I'm moving towards the next topic, that is free body diagram. Now, free body diagram is a diagram which is called as a graphical representation, okay, of a single or subsystem of bodies which is isolated from its surrounding but shown under the action of force. How it is? Say, for example, you have some ball, okay, some ball resting on the ground. It is resting on the ground means it doesn't mean that there's no force acting on it, because as we see in the previous case, if any body is said to be in the state of rest means it should undergo all sorts of force, but still the resultant should be equal to zero, then the body will be under the state of rest. So on that basis, if I take for this body, if you see, you it will have its own weight, say w. Even though it has its own weight, it's not sinking inside the earth because there is one normal reaction from the earth. So these two will be equated. That is, if you apply summation fy equal to 0, your w is equals to n. Only when w is equals to n, the body will not sink inside or will not bounce above the structure. That's when the body is under the state of rest. So how to represent this? When you're going to represent this, you're not going to write the surrounding, that is this ball. When you're going to represent this to analyze in a problem, all that you're doing is just write that point, okay, where both the forces are meeting, write the bottom force, normal reaction, and the top force, that is the weight. Only these things you are going to write. What is this? This is a graphical representation of system or subsystem. Here I have taken the total system, only two forces are acting, I'm taking two forces. System or subsystem of forces, and isolate it from its surrounding, remove the surrounding, whether it is wall, whether it is a groove, whether it is earth, remove from its surrounding and show only under the action of force, then it is called as free body diagram. I have taken certain example for that. Firstly, a boy who is swinging on a swing, if you see here, he has his own mass, and the two ropes are trying that, ensuring that the body is not moving down, because since he is staying in the state of rest, it means that he is under the state of rest, means his force, whatever is applied on him, I can show like this in the free body diagram to analyze how much force that is taken by the rope. We can analyze this by applying equations of equilibrium. To analyze the structure, that is what how much force that we may require in this rope to keep the system in equilibrium, we have to write free body diagram. So this boy is modeled into free body diagram through this. So this is one of the example. If I take another example, that is a crane. So crane holding some amount of weight on one end. If you take, so I can write the free body diagram in such a way that one force is moving up, another force is moving down, and its own weight, counterweight is coming down. So this type we can explain, this is the free body diagram. So y-axis, x-axis will show like this. We'll exclude all the surroundings and will show only under the action of forces. That is our free body diagram. So now this is another example, that is ladder, where here ladder, at this point we have the friction of wall, we have the normal from the wall, and here its own weight is acting on its centroid or center of gravity, and we have friction at the bottom where we have the contact surface and a normal reaction from the earth surface. So this is the free body diagram, which is isolated from its surrounding, shown under only the action of forces. So let me give a brief introduction about the supports before starting the problems. So supports, there are four important major supports that we have in civil engineering, which we should understand. So these are the basic kind of supports. So the combination of this we can see in the higher semester subjects like steel, PSE, where my colleagues will be introducing all those subjects in the upcoming sessions. So I'm going to give you the basic briefs about the supports. So first support that I'm going to talk is about roller support. So roller support, I have shown you an example of cycle, which is a person riding a bicycle. If you see the roller, I am taking the example of a wheel of a bicycle. Observe this wheel. This wheel is moving towards left. That means this wheel is allowing the body to move in the x direction. Fx is allowed. Okay. Or I can say fx is allowed. Okay, fine. Another one, this wheel is rotating. Rotating about which axis? Observe, this is rotating about z axis. This is rotating about z axis. So that means it can rotate, it can move in the x direction. But see, but this wheel is not sinking inside the earth. Why it is not sinking inside the earth? It's because it's because there is a reaction from the earth exactly at this point, perpendicular to the wheel. Okay, that's why this body is not moving in the vertical direction. So roller supports offer reaction or offers resistance only in the vertical direction. So this is the reaction offered by roller support. So wherever you have roller support, the reaction will be offered only in the vertical direction. We often see such roller support in many structures. So one of the structure I have taken is a bridge support, where we have a roller support. So roller support offers reaction only in vertical direction. So this is how we graphically represent a roller support, where the roller support has only one reaction. Next, something like I have taken an example of a door here. So hinge support is something where this support cannot be moved in x direction. That means there is a resistance offered by the body in x direction. So I will call this as, say, HA, x direction. Okay, HA. And the same uh, door, it cannot be moved in the vertical direction like this, because there is a reaction from the vertical line. Say I'll call this as VA if this point is A. So I have two reactions. One is HA and one is Va, which these two reactions are making sure that or resisting that the body should not move from its original position either in the x direction or in the y direction. But observe, this body is rotating. In this case, since this body is having a dimension in x and y axis, and this body is rotating about y axis here, but in actual field, as I showed you in the previous cases, it will rotate about the z axis. So in a hinge support, usually you have two reactions, HA and VA, whereas the other reaction, that is other moment, the rotation is allowed at a hinge. So only two reactions at hinge. One is VA, another one is HA. Only two reactions at hinge support. That we should remember. Okay, now I'll move on to the next support. Before moving to the next support, we have certain example of it. So this is another bridge called Bascal bridge where it is hinged. Okay, even you can take the elbow, the knee joints and the elbow joints of a hand and leg, those have a hinge like support where we can have one end hinged, that is pinned, and the other end is moving. So we cannot just drag this point from its position in the x direction or in the y direction. All that we allowed is just the rotation. So only two reactions exist, both in the horizontal as well as in the vertical direction. So this happens in the same way as like in that of Bascal's bridge, or we call it as movable bridge. So this is pinned support, which is also called as a hinge support, where I said you have two reactions, HA and VA, if you call this point as A. The roller has only one reaction, RA. So next support we are talking is about fixed support. So fixed support, for fixed support, I have taken directly an example where the body is completely fixed. So one end is fixed here, the horizontal direction. At the same time, we cannot even rotate it. We cannot even try to rotate it. If you try to rotate, it certainly resists initially in its positions, but it will never allow the body to move here and there. It resists. So how many reactions we have? So we have a reaction which will not allow the body in the x direction, that is HA. The one which will not allow the body in the y direction to move, that is your VA. And the other one is the rotation. It will not allow the body to rotate, so MA. So totally three reactions we have. One of the most familiar support that we know is beam column joint. So beam column joints are usually fixed support, where each of this fixity will not allow the body to move in the horizontal direction, vertical direction, or to rotate on its original axis. So graphically, we represent fixed support like this. So we have horizontal reaction, vertical reaction, and a moment. Okay, that's for the fixed support. And lastly, I have given you one more support with a little space. Why? Because this it's called simple support. Simple support is actually not a structural support to that extent. These three are the structural supports, whereas simple support is something which is when the body is in contact with the other body, it simply exhibits certain amount of reaction. When the body is in contact with other body, it simply exhibits certain amount of reactions. If you see that, if I have taken a ball which is placed in a kind of groove where it is connected to three sides or three walls. Okay, if you take these three paper walls or cardboard walls that you have here, just it is attached, just it has touched the ball. So because of this touching, what's happening? The ball is not allowed to move in any direction. How many reactions are applied? See, in all the contact points, at its contact points, there is always a reaction like this. At its contact points, where it has contact towards its centroid, it will always have its reactions. Likewise, from the back side also, there will be a reaction like this to its center. So that's about a simple support. One more example, most famous, you have seen this example, the sitting bench in the park. If you see, this bench is also, if you see this columns, whatever we have, the small pillars like stone columns, and on the top the slab or a simple horizontal member is just laid, just placed. There will not be any kind of connections here. Okay, and that's why this body is called as simple support. This is called simple support. I am not telling this as a simply supported beam. I'm telling this as simple support. Just I'm giving uh, the lecture about the supports, not about the beams. Simply supported beam is different, whereas this is a simple support. So when we go to the further sessions in structural analysis, I'm going to explain you about the different types of beams where simply supported beam will come. But this is simple support. So at each contact points, there generates one reaction. So this is what I was telling. So simple support is always generated at the point where you have frictionless surface. So where you have frictionless surface, you'll be having only one reaction exactly perpendicular to the surface on which it is acting. That is the simple support. Now coming to the sign convention of force and moments before moving ahead. So now I'm concentrating only on two-dimensional structure. So I have to write MZ. Remember the sign conventions that I'm using here in this session is forces moving rightward is treated as positive, forces moving upward is treated as positive, and moments that is rotating about z axis in the clockwise direction is treated as positive. So clockwise moments are positive, rightward forces are positive, and upward forces are positive. These are the sign convention that I'm going to use it for force and moment. Now, moving to the next part. So, as we have come to the end of all the supports and principles, let me give. So the time is right now. It is 4:30, almost 4:30. So we still have 45 minutes more to cover few problems. So let me start with the very first problem. Let us try to write the correct free body diagram for this. So whatever the problems I have taken here, all are gate problems, previous gate problems. I'm going to solve around 12 problems in this session. Hope this 45 minutes is enough to complete this problem. Okay, so let me take the first one. Here I have to write the free body diagram of this. So make sure that here the body will be written like this. This is the force W. This is a roller support. At roller support, we have only one force. Okay. So at hinge support, we have two reactions, one horizontal, another vertical. So two reactions at the hinge support and one reaction at the roller support. So this is what we have for free body diagram. So let us see the options and pick the right one. So if you see the options, so in the very first one, we have two reactions at joint A and one reaction at joint B, and the force W is there. So according to this, whatever we have written is matching with this. So this works out to be the correct answer. But let's see the next one. See, this is applicable only when you have both the ends with roller support. And joint C is applicable only when you have A has roller support and B has hinge support. Okay, because two reactions at hinge. Now the D1 is applicable when you have both ends hinged. So that's why we can say that option A is the right answer. So for problem number 1, option A is the right answer. Likewise, one more problem was asked for 1 mark about the free body diagram. So this is the question. What's the free body diagram for this diagram? So the free body diagram is always isolated from its surrounding and shown under the action of forces. So this is the body we have. Okay, at this point, I'll write a force F, which is at an angle 60 degree with the horizontal. And at this point, I have one horizontal reaction because this is a fixed support, one vertical reaction and a moment. Let us observe which is having this type of reaction. See, at point A, we have for in the first figure, we have three reactions at point A and F is 60 degree. Okay, this is matching with our answer. I'll go to second answer. If you see the second answer, it is also having three reactions and F is equals to 60 degree. So this may also be an answer. I'll go to the third one. So it has only one vertical reaction and one moment. So horizontal reaction is missing. So this cannot be the answer. Coming to the D1, here the moment is missing, hence this is not the right answer. So which is the right answer? So if you see these two, both looks alike, but this is given with the support. Hence, this cannot be a right answer. Free body diagram is one where supports are not written. Support should not be written on the free body diagram. Hence, this is the right free body diagram. Okay, hope you people are understanding. I'll move to the next problem. So problem number 3, where they have told the resultant of two forces P and Q is R. So there are two forces P and Q. Okay, P and Q, something like this you have in certain direction, P and Q with certain angle theta, for which the resultant is R. If one of the force, any one maybe, I'll take P only, if the direction of force P is taken in the opposite direction, is reversed, then the resultant instead of R, it will become yes. If I have to prove this true, then what should be the angle between these two forces? That's the question. Which of the following is true for the identification of r square minus s square is equals to 2pq? Let's find out this theta first, for which I'll write the formula. When two forces are acting at a point, there are two methods. Okay, what is the first method? As I told, summation of x square plus summation of y square. That's the one of the method. The other method, when only two forces are acting at a point and separated by a certain fixed angle, then you can apply parallelogram law. So all of us know parallelogram law, which is also most famously called as cosine rule. So I'll apply that cosine rule here. See, r is equals to p square plus q square plus 2pq cos theta. This is the formula we have. Okay, so instead of square root, I'll put r square. Okay, so this is when the forces are moving in this original direction. If one of the forces reversed, means it has become, instead of plus p, it has become minus p. So I will write p square plus q square minus 2pq cos theta. Then the resultant will become s square. The equation is this: r square minus s square is equals to 2pq. Let us check. Now I'll do r square minus s square. If I do r square minus s square, this will become minus, minus, this will become plus. These two things will go. This will become 4pq cos theta. Okay, so 4pq is there, cos theta is also there. If I make theta is equals to make this equal to 2pq, I have to make cos theta is equals to half. If I make cos theta is equals to half, I'll get 4. To make cos theta is equals to half, theta will become 60 degree. Cos inverse of half is 60 degree. So the thing is, force are collinear. If both are collinear, this cannot happen. Force act at right angles, that is theta is equals to 90 degree, it cannot happen. Force act at 60 degree to each other. This holds good only when force between these two forces are equal to 60 degree. Hence, C is the right answer. The force can have any angle of inclination between them. So this cannot be happening, because see, if cos theta, this if I put theta is equals to 0, then it will become 4pq, or if theta is equals to 90 degree, it will become 0. Okay, so this cannot happen. So the answer should be forces act at 60 degree to each other. Forces act at 60 degree to each other. Now moving to the next problem. So I'm going to the next problem, like problem number 4. A known force R is to be replaced by two forces P and Q parallel to the R, and at a distance A and B from R as shown in figure. So figure is given. I have to find force P. I have to find force P. So to find force P, here I am starting with the equation of equilibrium. We have three equations. I'll apply only one. I'll call this as point B, this as point A. I'm going to apply moment about point B is equals to 0, considering clockwise moment positive. So we know that this equation tells that it symbolizes that algebraic sum of moments about any point on the rigid body is equals to 0. On the body is equals to 0. Now what is it? B indicates, B tells that take about point B. I can make this formula hold good about point A. This formula holds good about this point of R, anywhere in between also. But I'm taking here because if I take here, the moment due to Q will become 0. So I'll get directly what is P. So about point B, P is rotating like this. P is moving in the clockwise direction. So I'll put plus P into the distance from A to B, or you can say B to P is A plus B. So I will write A plus B. So this is moment due to force P. So we have F into D, force into distance. We have taken moment. So about point B, another force I have is R. R is moving like this in the anti-clockwise direction. So I will write minus force is R into distance from point B to R is B. No other forces. This is equal to 0. I want P. I'll keep P this side. This goes to that side. RB divided by A plus B is the right answer. So RB divided by A plus B is the right answer. Okay. I'll go to the next problem now. Problem number 5. So problem number 5 says that a box of weight 100 kilonewton. Now, this question is a little bit tricky. See, whatever the problem I'm solving, I may be moving a little bit faster. You can slow down and read it or observe, understand the concept that I'm teaching, and then crack the problems easily. Now I'm going to problem number 5, where the problem looks quite difficult, quite twisted, but actually easy problem. So all the problems in gates are usually like this. So what they have told, a box of weight 100 kilonewton shown in this figure is to be lifted. This 100 kilonewton block has to be lifted without any kind of swing. That means it has to be moved exactly in the vertical direction like this. This is the direction of resultant. Okay, without any kind of swing, it has to move up. It has to be lifted up. If all forces are coplanar, all forces are in the same plane, the magnitude and direction of theta of force F with respect to x-axis should be, we have to find F and theta. Okay, the condition we know is that the resultant R is moving exactly vertical. So I have taken the figures separately. Let me write the free body diagram first. So we have x-axis, we have y-axis, x, y, the very first force here, F with an angle theta, and 40 kilonewton with an angle 45 degree, and this side I have another force 90 kilonewton at an angle 30 degree. So first step is to resolve, next step is to combine to make summation fx, summation fy. But here one of the most important condition we should remember is that the resultant R should be pulled in the upward direction like this. R is purely vertical, that is 90-degree angle, and it has to be pulled up. See, if you want to pull up this R like this, resultant, if you want to pull 100 kilonewton, then you should put a load equal to 100 kilonewton. So if you want to lift a load of 100 kilonewton, you should put a load equal to 100 kilonewton. Therefore, directly the formula goes like this: R is equals to 100 kilonewton. And observe, if the R is purely vertical, the angle made is 90 degree. With that, okay, so our basic formula is summation Fy is equals to what? R sine theta. R sine 90 is equals to R, and summation Fx is equals to R cos theta, which is directly equal to 0 because cos 90 is 0. So the two conditions that you should remember is r is equals to summation fy and summation fx equal to 0. Okay, and remember one thing, here r is moving in upward direction, therefore summation fy is plus r, not the minus r. So keeping these two equations, we will find what is f and what is theta. So let me take the first equation, that is r is equals to summation fy. So I have to take all the vertical components. So vertical component of f comes here. So it is f sine theta. So I have to take vertical component, that means which is not adjacent to angle, it is always opposite to angle. So I'll take all the sine components. Then we have 40 kilonewton, which is again moving above the x-axis, means positive y-axis, plus 40 sine 45. 90 is also moving upward here. Okay, vertical component of 90 is also positive, plus 90 sine 30 is equals to 0. Therefore, f sine theta is equals to. So let us calculate and write f sine theta is equals to, we will get around 26.71 kilonewton. Okay, and likewise, if I apply the second equation, 1 minute, I have made one mistake here. So simple, f sine theta plus 40 sine 45 plus 90 sine 30 is equals to r. R is what? 100 kilonewton. So if you substitute, if you take these two things to this side, f sine theta will become 26.71 kilonewton. Likewise, if I take summation fx equal to 0, rightward forces as positive, I will take plus f cos theta, because for the first it moves right like this, second also it moves right, for this it moves left. So f cos theta plus 40 cos 45 minus 90 cos 30 is equals to 0. With that, f cos theta value that I have calculated is 49.65 kilonewton. So these are the two values we have. Let me call this as equation 1 and this as equation 2. Just do 2 by 1. Equation 2 by 1, you will get tan theta. So tan theta will be 26.71 divided by 49.65. So if you do that, you will get theta is equals to around 28.28 degree. And if you substitute theta back to f cos theta or f sin theta equation, so your f will be equal to 56.37 kilonewton. You can check it once in the calculator to get the right answer. So I have checked once, and this is the answer for this problem. So the answers that we have given with in GATE is this. So answer we have is 56.37 and at an angle 28.28. So the first one is the right answer. So both are positive. First one is the right answer. Now I'll move to the next problem, problem number 6. A weight of 50 Newton is supported by two metallic ropes as shown in the figure. See here, I have to apply equations of equilibrium. This is a problem on equations of equilibrium. I have two options. Either I can apply equation of equilibrium or Lami's theorem. I'll tell you what is Lami's theorem. Before that, let me complete this. The weight of 50 Newton is supported by these two metallic ropes. We have to find what is T1 and what is T2. That's our main intention. So let me solve this problem. Before solving, let me talk to you about Lami's theorem. So Lami's theorem states that when three forces are acting simultaneously on a body such that all three forces are concurrent, coplanar, and emerging out of the body. Remember, we have to write the free body diagram to apply the Lami's theorem in such a way that the forces should emerge out of the body. So emerging out of the body, then each force, I will call this as P, Q, and R. Opposite to P, I'll write alpha. Opposite to Q, I will write beta. Opposite to R, I will write gamma. So all that will say that, So if three forces which are coplanar and concurrent and all are emerging out of one point, then each force is directly proportional to sine of angle between the other two forces. So if you want this sine of angle between other two forces means I have considered force P, so leave P, angle between R and Q is alpha. So P is directly proportional to sine alpha. So this is Lami's theorem. So from Lami's theorem, removing all the proportionality constant, I will get P divided by sine alpha is equals to Q divided by sine beta is equals to R divided by sine gamma. So this is the formula we have. So we have certain conditions for Lami's theorem. Remember, Lami's theorem is applicable when only three forces are acting at joints. It is only for three forces acting at one single joint. That's one. Second one, in these three forces, at least one force should be known. If at least one force is known, then we can apply this equation. Or I can say it should not have more than two unknowns. The joint should not have more than two unknowns. If the joint is having more than two unknowns, you cannot apply Lami's theorem. Okay, remember these conditions for Lami's theorem. So let me remove all these things. I will consider this formula and solve this problem. So to solve this problem, I should consider the either equations of equilibrium or Lami's theorem. But in a hurry, in while writing the examination, it's better you apply Lami's theorem. So to apply this, first I have to write the free body diagram of this. So you have 500 Newton force, which is moving downward. And see, this is the tension force. To exhibit tension, always remember tension is a force which always acts away from the joint like this. If these are the two joints, away from the joint, forces will act. All that you should do is you cut here, write this as a separate free body diagram. Okay, 500 Newton, this is T2 and this is T1. Observe the angle between these two is 90 degree and the angle between these two is given as 120 degree. When this is given, just hold your calculator and check what is 360 minus 120 minus 90. So it is 150. So this angle is 150 degree. I'm applying this equation. In place of P, I will write 500. So 500 divided by opposite side is, so opposite to this forces, you have 90 degree. This divided by sine 90 is equals to Q. In place of Q, let me write T1. T1 divided by opposite to the T1, I have 120 degree. All that you should know is, if you write T1, forget T1. Check other two forces, angle between the other two forces we have to take. Sine 120 is equals to T2 divided by sine 150. So all that we are doing is equate T1 and 500 Newton components. So you'll get 500 by sine 90 is 500 only. 500 into sine 120 is 433. T1 is equals to 433.01 Newton. And equating this with this, you will get, so 500 into sine 150, you will get 250, which is equals to T2. So the answer for this problem is EA, 433 Newton and 250 Newton. You can see that's the right answer. So that's about the problem number 6. So we have in engineering mechanics another 6 problems to go. So problem number 7. So problem number 7 is the same type of problem where three forces are meeting at one joint. And as I said here, the force here, because of 100 Newton tries to drag the rope down, because of which the ropes here, AB and BC, are under high tension. So tension means force should move away from the joint like this. Force should move away from the joint. So cut here to write the free body diagram. Okay, we will cut there to write the free body diagram. So here also I can write like this, cut here. Okay, I'll write separately This is force in member BC. This is force in member AB. This is 100 Newton. Let me see what was the question clearly. Two identical ropes supports, there's a space here, supports a load of 100 Newton as shown in figure. The length of each rope is 1 meter. So the each rope length is given as 1 meter and 1 meter. Cross sectional area is 200 mm square for both, and E is equals to 200 GPa. The question asked is to find the force in rope AB in Newton, for which is just a question which is a little bit given, made confused with given with the lengths, areas, and Young's modulus. You have to find simply the force in rope AB, for which let us apply Lami's theorem. So again, I'll go to Lami's theorem. I just observe the angle given here is 30 degree. This is also 30 degree. Let me change the pointer. Okay. If this is 30, what is this angle? So this will become 120. 90 minus 30, 120. Here also it will become 90 minus 30, 120. So 360 minus 240 is again 120. So it's easy observe. Now I'm applying the same Lami's theorem. 100 divided by sine 120, 100 divided by sine 120 is equals to FAB divided by, see, after FAB, we'll remove, I will leave FAB and take the angle between other two forces. So sine 120 is equals to FBC divided by sine 120 again. See, all are 120, I will remove. So you can straight away tell FAB is equals to 100, FBC is equals to 100. So the answer is force in rope AB is 100 Newton. So this is the answer we have for problem number 7. Now moving to problem number 8. So here I have not given any introduction about the friction, but I have taken a problem on friction. So only condition that I have to tell here is about coefficient of friction, which is most popularly known as mu. Okay, mu is called coefficient of friction. Okay, mu is also called as tan theta or tan phi, and it is F by N. So F is always equal to mu times of N. So this formula you should remember, mu is equals to F by N, or I can say F is equals to mu times N. This is the only thing that you have to understand. All other things are already spoken, and be sure that when you're checking or when you're writing a friction problem or when you're attempting a friction problem, make sure the direction of friction force. So here they said find the value of tension acting in the cable. This is the cable as shown in the figure. Coefficient of friction for all surface is equal to 0.2. Weight of block A and block B is 4 kilonewton and 6 kilonewton. So block A, block B weight is given. Some weight P is applied here. P is applied towards left. Because of this, at these two junctions, the reactions or the frictions will be developed in the towards right. When you come to point A, at point A, the rope tries to drag or keep the body in equilibrium, so it drags back. It is under tension. It drags back like this. Once it drags, this body will develop a friction in the opposite direction. Okay, so friction here is above the surface. This two should be equal and opposite. Then only the body is under rest. Remember that. So here I can write two free body diagrams. So let me take the first one. I will take first one. I think that is enough because in that only I may get the answer. Say this is point A. Block A, okay, block A is having a weight of, what's the weight? 4 kilonewton. Block A is having a weight of 4 kilonewton, and there is a tension force here. Okay, tension means force should move away from the point, so I'll cut here. This angle will come. I'll call this as T. This angle is given as 45 degree, And at this junction, as I told you, because it drags like this, at this junction, force of friction develops in this direction. So I will call this as F. And since 4 kilonewton is applied, this body tries to move down on block B like this because of its own weight, tries to move down, but block B tries to arrest or resist the motion through offering a reaction in the opposite direction. So it is above. The reaction is above like this. I'll call this as a normal reaction. So we know that F is equals to or I can say mu times of N, or F is equals to 0.2 times of N. This is the F value we have. Keeping these three forces, all that I need is to find what is tension T. Let me find tension T. Okay. Firstly, let me apply the first equation, summation Fx equal to 0, rightward force is positive. So first I will apply T cos 45. That's the horizontal component, which is positive. This is a purely vertical, so no horizontal reaction. This is also purely vertical, no horizontal reaction. Only horizontal another we have is F, which is moving towards left, hence I'll put minus F, or I will directly write 0.2 times of N is equals to 0. Or I can call this as T cos 45. Okay, T cos 45 is equals to 0.2 times of N. Okay, this is one of the reaction that we have to find. Okay, I will call this as equation 1. Then I have summation Fy equal to 0, upward forces treated as positive, for which I will write here T sine 45 minus 4 plus N equal to 0. See, this is a purely horizontal force, plus T sine 45 minus 4 plus N equal to 0. Or I can write T sine 45 is equals to, if I take this 4 minus N, it will get. Okay, if I take these two, I'll call this as equation 2. If I make 2 equation 2 by 1, I will get uh, tan 45. Tan 45 is equals to 4 by N divided by 0.2 times of N. So tan 45 is 1. So if you cross multiply this, it will become 4 minus N is equals to 0.2 times of N. If I take to this side, 4 is equals to 1.2 times of N, and N is equals to 4 by 1.2. So 4 by 1.2 is 3.33. Okay, 3.33 Newton is the normal reaction that we have. Kilonewton is the normal reaction that we have. So I'll substitute back to any of these two equations. Say I will substitute to equation 2 only. T sine 45 is equals to 4 minus N is 3.33. With that, T is equals to, so 4 minus 3.33 divided by sine 45. So that will amount to 0.94. So around 0.948 you will get. So this is in kilonewton. So our answer was supposed to get the P value. Question asked is to find the tension. So I'm not going to take another block. Okay. If the question is asked to find what is P, then you should continue with the another force. So you have to stop only at this stage. So let me see the answers that was given. So answer that was given is 0.17, 0.95, 0.3, and 0.67. So we have this answer. 0.95 kilonewton. So that's the right answer. This is about problem number 8. I'll go to problem number 9 now. So the next problem also talks about equations of equilibrium, but see here we have at one joint we have 4 ropes connected. 4 ropes means 4 forces. What's the question? As for the system in equilibrium shown, the value of T1 by T2 is. So I have to find what is T1, I have to find what is T2, then divide T1 by T2, find out what is the answer of T1 by T2. So I will take the problem now. I will write the free body diagram. So I'll first come to joint E. See, when you have a frictionless and dropped here. Okay. See, because of this 100 Newton, this rope is under tension. That means force should move away from the joint. And this value is equals to 100 Newton. So as it moves here, again this is a rope, it is under the tension. The value simply transferred 100 Newton. Here also the rope, 100 Newton. Tension force that comes directly here just by applying summation Fy equal to 0. You come at this joint, since it's a frictionless pulley, it directly moves here. For in the frictionless pulley, the whatever the force you have in a rope will be transferred across the pulley directly. So this is also 100 Newton. Now I will take this joint. In that joint, we have T2 here. I'll cut at this junction and I will write the free body diagram. So one force is moving like this, 100 Newton, other moving like this, 100 Newton. The angle given here is 30 degree. Okay. And then the question is moving like this, T2, and this is another question, T1. So this is 60 degree, this is 45 degree. Okay. So these are the forces we have. We have to find what is T1, what is T2. We have to see at a coplanar point. So if you have coplanar concurrent force system, in the three equations of equilibrium, summation Fx equal to 0, summation Fy equal to 0, and summation Mz equal to 0. In this, since all forces are acting at the same point, moment concept will not come. Only two equations are valid. So I will take the first equation, summation Fx equal to 0, rightward force is treated as positive. For that case, I will apply here plus 100 T2, horizontal component of T2 plus T2 cos 60. T1 is moving towards left, so minus T1 cos 45. 100 Newton is moving towards left, so minus 100 cos 30 equal to 0. Or I can write minus T1 cos 45 plus T2 cos 30. And if you add these two, minus 100 and this value, you will get to this side, you will get minus 13.39. I'll call this as equation 1. And then you have summation Fy equal to 0. Upward force is treated as positive. If you take that, I can write here, see, vertical component of 100 Newton will become 0. Vertical component of T2 will become plus T2 sine 60. This will become plus T1 sine 45. And the last one is minus 100 sine 30 equal to 0. So 45 plus T2 sine 60 is equals to 50. So 100 sine 30 is 50. I'll call this as equation 2. Just by solving equation 1 and 2, you'll get T1 is equals to 37.88 kilonewton and T2 is equals to 26.8 Newton. So it's everything is in Newton. So with that T1 by T2, if you do it in calculator, you'll get around 1.41. So the answers, if you see, these are the answers we have. So C will be the right answer. That is 1.414. Yeah, that's one of the question. Now moving to the next question, that is problem number 10. A rigid ball of weight 100 Newton, this is the 100 Newton weight, is suspended with the help of a string here. Okay, this string, is applied or pulled by a horizontal force F, such that string makes an angle 30 degree with the horizontal, with the vertical. The magnitude of force F I have to find. So let me write this figure. So free body diagram is right away there. Let me change the color. So here, because of this ball weight 100 Newton, this rope is under tension. So I will cut at this point and find out what is the free body diagram. So this is the free body diagram. I will write the free body diagram. This is T, this is F, this is 100 Newton. This angle I have to find. See, they have given angle with respect to vertical. See, if this is 30, this is also equal to 30. If this is 30, this is equal to 60. So I'll write that is equal to 60. So what's the question asked? Question asked is to find what is the magnitude of F. To find the magnitude of F, let me find out all other values also. So I will write summation fx is equals to 0. So this is 60 degree, fx is equals to 0. If you apply that, horizontal force towards right is positive, plus f minus t cos 60 is equals to 0. You don't know the value of t cos 60, so keep it as it is. I'll apply another equation, summation fy equal to 0. Upward force is positive, so I'll get t component which is moving upward, plus t sine 60, 100 is moving downward, minus 100 equal to 0. With that, t is equals to 100 divided by sine 60. The answer you're going to get is 115.47. Therefore, f is equals to, so t cos 60, you will get around a 57.7 Newton. So let me see the answers if we have that f. So yeah, f value we have is 57.73. This is the right answer for F. So this is problem number. Then I'll move on to the next problem. So this problem was given in the mock test that we had yesterday. So the magnitude of forces P, Q, and R. We have three forces here: P, Q, and R. 100, 250, 150. The respective values of magnitude and directions of the resultant force, okay, R. So the resultant force we have to find. For the resultant force, I have to find what is magnitude and direction. Magnitude is nothing but R value, direction is nothing but alpha value. Let us find that. So I will take this. So before moving, let us read again. P is equals to 100, Q is equals to 250, R is equals to 150. 100, 250, 150. Is that Newton? No, kilonewton. So let me change this to kilonewton. Okay. So let me write the free body diagram once again. Just observe how I'm writing. Writing free body diagram is important. Once you write the free body diagram, everything will be over. See, x axis, this is force P. I'll straight away write as 100 kilonewton. This angle is given as 60 degree. Another force here, okay, is somewhere here like this. Okay. This is 250 kilonewton. They said the angle between this and this force is 45 degree. So let me see what is this angle. So that angle is 60 plus 45 degree. 60 plus 45, we are going to get 105. 105 means, let me write this angle. It's easy for me to write this angle. 180 minus 105 is 75 degrees. So this angle is given as 75 degree with respect to x-axis. So another force is here, moving here R. So the angle between Q and R is 90 degrees. So already we have 75 degree. The remaining angle is 15 degree. So I'll write 15 degree here, and this is equals to 150 kilonewton. So we are ready with the angles with respect to horizontal. Now all that we can do is split and add to the equation of R. So here we go. Summation fx equal to 0. Sorry, not 0. We have to find this. So let me start with summation fx, which is moving towards right. 100 cos 60, which is moving towards right, is plus. 250 is moving towards left, minus 250 cos 75. And R is also moving towards left, so minus 150 cos 15. So we have to find summation fx. So we'll find it. 100 cos 60 minus 250 cos 75 minus 150 cos 15. The answer is 100 and minus 159.59 kilonewton, which clearly indicates that summation fx is moving towards left. I'll go to summation fy. It starts with 100 sine 60 plus 250 sine 75 plus, not plus, this time it is minus. So minus 150 sine 15. So what's the value? 100 sine 60 plus 250 sine 75 minus 150 sine 15. So the value is 289.26 kilonewton. So this is summation Fy. With that, this summation Fx and summation Fy, see summation Fy is positive means it's moving upward. So this is a leftward force, this is an upward force. Summation Fx, summation Fy. Now resultant R is here. Okay, and the alpha that they are asking is with respect to x-axis, positive x-axis, then this is alpha. Of course this is also alpha, but this is with respect to x-axis, this is with respect to positive x-axis. So let us find both the angles. So let me write this first. So according to this, R is equals to square root of summation Fx square plus summation Fy square. We do that, 159.59 square plus 289.26 square under root, you're going to get R is equals to 330.36 kilonewton. And alpha, so if I call this as theta, theta is equals to simply tan inverse summation Fy by summation Fx. If you do that, you will get an answer of say 289.26 divided by 159.59, 1.81 you will get. So tan inverse of 1.81 will become 61.11 degree. That is your theta. I want alpha, that is with respect to x-axis, positive x-axis. So that will become 180 minus 61, that is 118.88 degree. So let me see if this answer is available. 330 and 118.9 degree or 88 degree. So that C is the right answer. And I'll take a last problem. We are left with last 3 minutes. I'll take a last problem. That is, this is also given in the mock gate exam. An assemble made of a rigid arm ABC hinged at A and supported by an elastic rope CD and CD at end C. Now here this is hinged, they said. Okay, the members may be assumed to be weightless and the lengths of the respective members are as shown in figure. So what is that we have to find? We have to find the force in the rope. The force in this rope we have to find. So let us find what is the tension in this rope. So because of this force, it tries to drag it back, hence it may be under the tension. I'll consider this as under tension. Of course, there is another force that is there here. I'll take this joint and I will write the free body diagram of that joint, So one force is moving like this. I will call this as force in the member BC. Another force is in the tension in the rope. So this is what we have to find. And given that this is force P. So this angle I want first to find out what is T in the rope. So this angle is simply, you observe this, opposite side is L, adjacent side is L. So since both are equal, this angle will be equal to 45 degrees. So if I take this as 45 degree, simply I will apply summation Fy equal to 0. Upward force is treated as positive. So, this P is moving down, so minus P. This T of rope is moving up. So I will write plus T sine 45 equal to 0. With that, T is equals to, P divided by sine 45. So sine 45 is equals to 1 by root 2. So when it comes up, T is equals to root 2 times of P. So observe the answer. Our answer is D. D is the right answer. So with that, I have finished a brief introduction about what is mechanics, and have solved few problems on this. So what I would like to say total overall is engineering mechanics is not a simple subject. It's a prerequisite to many structural engineering subjects. So it's very important for you to understand these engineering mechanics first. So afterwards, the solutions to the problems are based on basic concepts that I have told you, and few more concepts I have told you in between, like Lami's theorem, parallelogram law, And I have missed one more, that is Varignon's theorem. If possible, I'll cover it in the next upcoming session. So you have to understand these basic concepts and fundamental principles. You will not be asked very much questions on the concepts, but based on the concepts only, problems will be asked. So question will be highly twisted. Sometimes it looks twisted, but the solution will be very, very simple. So crack the question by understanding the concepts and solve the problem as soon as possible. Don't waste the time further. So thank you for your patient listening, and I hand over the session to the session chair, Professor Raghavendra. Over to you, sir.
Madam, the session was very much understandable, and I hope every participant has got a better knowledge about the session today. And it was indeed a very fruitful session. And thank you very much on the behalf of each and everyone who have got benefited from the session. Thank you very much.
Thank you, sir.
And to the participants, the day 2, session 1 will be starting at exactly 2 p.m. tomorrow. And please stay tuned. Thank you.